Hello, everybody. It's Professor Ken presenting to my beautiful calculus students today. It's November 16th, and this is the slideshow for November 16th. I promised you it would be posted at 11. It's after 12 already, so I'm quite late. I apologize for that. Okay, and away we go. So I'm going to stop my little video part so you don't have to, my face doesn't get in your way while I'm presenting. Okay, this is going to require a lot of thought, so you need to be on top of your game here. All right, we got our little turkey there. So today's November 16th, Calc 1. All right, now we want to activate our prior knowledge first of all. So a derivative is a slope of a tangent line at a point on a graph, which we should know already. But the word slope, now before I say that, the graph may be a function or a relation. It could be a straight line, it could be a curve, it could be a circle, it could be anything. Anything that has points, every point has a tangent line. So the slope is a rate of change. And the little letter D in calculus means the change in. So by the property of transitivity, if a derivative is a slope and a slope is a rate of change, then a derivative is a rate of change. So dy over dx is a way to express a derivative. It means the rate of change of y over the rate of change of x. So we've done all this already. So this technically means the change in y over the change in x. In other words, the slope. Okay, look at this square. Each side is length x. Rates. Now, when we're dealing with rates, we're dealing with time. So derivatives don't have to be expressed in just dy dx. Let's look at the area of a square. If a, the area, equals x squared, this means that now, I don't know why I keep putting accents on my a's. I don't know what the hell setting is on, but if the area of the square is equal to the length of one side squared, a equals one side squared, then we could take the derivative of both sides, and we get dA, because the derivative of a is dA, the derivative of x squared is 2x dx. So dA equals 2x dx. We could divide both sides by dx, and we get the rate of change of a with respect to x is equal to 2 times x. Now, this means the rate at which the area grows with respect to the length is 2 times the length, which really doesn't mean a whole heck of a lot, all that much. Because when I think about rates, I think about time. So this slide right now is supremely important. So if the area is equal to x squared of this square, when we talk about rates, time is involved. When we have a formula like a equals x squared, and one of the variables has a rate of change using time, like miles per hour, we now have 3 variables. So for instance, we may say that the sides of this square are growing at a rate of 2 inches per second. So we have the area in square inches, we have the sides in inches, and we have the rate at which the sides are growing, which is inches per second. So the independent variable is x, the dependent variable is y, and time is t. Now, we don't see time in this formula right here, but we did say that it's growing, so that requires time. So we don't want to know the rate of change of x with respect to the rate of change of a with respect to x. In other words, we don't want to know dA dx or dA over dx. We want to know the rate of change of a with respect to time. We want to know dA over dt, because that would be like inches squared per second. So moving along here, this is called related rates. So if a equals x squared, the area is equal to one side squared. When we introduce the rate of change with respect to time, the denominator of the rate of change is dt. So suppose the sides of the square are growing at a rate of 4 inches per second. We would say that the change in each side with respect to time, or dx over dt, or just dx, even though it says dx over dt, we just call it dx dt, is 4 inches per second. So how fast is the area changing when the sides are 5 inches long? Oh, here's where we have some fun. I'm getting very excited. So how fast is the area changing when the sides are 5 inches long? Well, we already know that the formula for area is x squared. We take the derivative of both sides with respect to time. So the derivative of the left side isn't going to be dA, isn't going to be just dA, it's going to be dA over dt. And the derivative of x squared isn't going to be 2x dx, it's going to be 2x dx over dt. So if we go back to this slide right here, look at this part right here. Basically, I just divided both sides by the dt. So dA over dt equals 2x times dx over dt. That's all I really did. Slideshow. All right, we talked about that already. All right, related rates. All right, so it's growing at the sides are growing at 4 inches per second. So dx over dt, dx dt equals 4 inches per second. How fast is the area changing when the sides are 5 inches long? Remember, the sides are 5 inches long. So area equals x squared. So dA dt equals 2x dx dt. That's just implicit differentiation with respect to t. So in the previous slide, we learned that dx dt was 4 inches per second. All right. So look at this, folks. We also know that each side is 5 inches. Look up here, 5 inches long. So we don't know dA dt, but that's how fast the area is changing. How fast the area changes. So that's what we want to know. We do now know x. X is 5 inches long. And we also know the rate of change of x, 4 inches per second. So now we just plug and chug. We take these values for dx dt, and for x, we plug the x value in here. We plug the dx dt value here. And what do we get? We have dA dt equals 2x dx dt. Plugging it in, we have dA dt equals 2 times 5 inches times 4 inches per second. So what are our units? Well, we measure area in inches squared. So we would measure the rate of change of area in inches squared per second. And that makes sense because inches times inches is inches squared over seconds. So 2 times 5 times 4 is 40. So the rate of change of area with respect to time is 40 inches per second. What does that mean? The area is growing at a rate of 40 square inches per second. Let's say inches. Quickly save there. Okay, so now I'm going to the next slide. Now, here's another way to think about it. Suppose we have the area. Okay, look at this right triangle. We see that one side is A and one side is B. Now, a right triangle is half of a rectangle. Look at this. So if I made another one of these right triangles and flipped it, we would have a rectangle whose length is B and width is A, length is B. So since a right triangle is half of a rectangle, the area is 1/2 A times B. So we have over here the area of that triangle is 1/2 A times B. The small leg, suppose now, the small leg is growing at 4 inches per minute, this side right here. And the big leg is shrinking at -2 inches per minute. Well, go back to this original. We can now take the derivative of this equation. So the derivative of A is dA dt. We just bring down the 1/2, and then we use the product rule. A times B would be 1 d2 plus 2 d1. So we know that dA dt right over here is equal to 4, and dB dt is equal to -2. So we can make a table. We could just pick any length and any width. We would do length times width divided by 2 to get the area. That's this formula up here. And then to get the rate at which the area is growing, we would use this equation right here. dA dt is the length at which the area is growing. We do 1/2 times the A values, which are right here. I made a formula, times dB dt. Whoa, no, I don't want that. Times dB dt, which is -2 all the time, plus the B value, which are these values right here, times dA dt, which is +4 all the time. So the area is in square inches, and the rate at which the area is changing is square inches per minute. So how would we do the first line? It would be equal to 1/2 times. Okay, 2 times -2 is -4. 5 times 4 is, oh my gosh, I forgot to divide it by half. I have to change this. All right, it's all right. All right. The legs, now this is a new problem. The legs of an isosceles right triangle increase in length at a rate of 2 meters per second. Now, isosceles means the two legs are equal, so we call them both x. How fast is the area growing if the legs are 5 meters long? So on the left-hand side, I'm going to draw a picture and write all the formulas I know. Well, using the Pythagorean theorem, I know that x squared plus x squared equals the hypotenuse squared, which we'll call h. So if I get h by itself, by taking the square, x squared plus x squared is 2x, take the square root of both sides, we get h is equal to the square root of 2x squared. But the square root of x squared is just x, so h is equal to the square root of 2 times x. And the area is equal to, remember, it's half of a rectangle. So if it was a rectangle, it'd be x times x or x squared. Since it's half of that, it's 1/2 of x times x or x squared. So the area is 1/2 x squared. Now, the rate of change of x with respect to t is 2 meters per second because it's growing at a length of 2 meters per second. Now, we want to know how fast is the area growing. So we're going to use the area formula. Now we're going to take the derivative of the area formula. And we get the derivative of a is dA dt. 2 times 1/2 is just 1. So we don't have to have anything. Then dx and dx dt. Now we know x is equal to 5 meters. It says it up here. And dx dt is equal to 2 meters per second. It says it up here. So our dA dt, we're going to plug and chug. X is 5. Dx dt is 10. And what units is that? Units are very important. So we say the area of the isosceles right triangle is growing at a rate of 10 square meters per second. I think you should pause right here and take some notes. I'm going to not pause, though. All right, here's the same information. Now we're changing it up a little bit. The legs of an isosceles right triangle increase in length at a rate of 2 meters per second. At what rate is the hypotenuse changing when the legs are 5 meters? So now we're going to use this hypotenuse formula right here. So a hypotenuse equals the square root of 2 times x. Take the derivative of both sides. dH dt is equal to, well, the derivative of this side is just the square root of 2, and then we tack on the dx dt. Now we're ready to plug and chug. We know that dx dt is equal to 2 meters per second. And we don't have any, it says when the legs are 5 meters, but that doesn't matter because we don't have any more x in our formula. So plugging it in, we get the square root of 2 times dx dt is 2. So that's 2 square roots of 2 is dH dt. Now, this hypotenuse, the length of the hypotenuse is in meters. So our units won't be meters squared per second, just meters per second. So the hypotenuse is growing at a rate of 2 square roots of 2 meters per second when the lengths of the legs are 5 meters. It's a pretty house. All right, so steps to solving related rates problems. Number 1, after you read the problem, draw a picture. Write down all the given information. Write down as many formulas as you can. And look at what the problem is asking and select the appropriate formula. Then after we do that, use implicit differentiation with respect to time t to take the derivative of the formula that we selected. Write down our known values again, plug and chug, and write our answers with the appropriate units. How do we know the appropriate units? If we're dealing with area, it's going to be units squared. If we're dealing with volume, it's units cubed. And then finally, be sure you answer the question. That's usually with words. All right, look at this circle. All right, so it says the area, we're going to use that 9-step process now. The area of a circle increases at a rate of 3 centimeters squared per second. That's area. How fast is the radius changing when the radius is equal to 5? All right, so there's 2 formulas. We drew a picture. There's 2 formulas for a circle. One is the area formula. One is the circumference formula. For this problem, they're asking about the area. So when we write down the information that they give us, we know that the change in area with respect to time is 3 centimeters squared per second, and the radius is 5. So we're going to use that area formula. Area equals pi r squared. Now we're going to take the derivative of both of this equation, or both sides. So the derivative of a is dA dt. The derivative of pi r squared would be 2 pi r dr dt. There we have, we take that 2, throw it in front, subtract 1, and tack on the dr dt. Now we can plug and chug. dA dt is equal to 3, r is equal to 5, and we're trying to find dr dt. So we have substitute in the 3, substitute in the 5, and this is equal to 10 pi. So 3 divided by 10 pi is equal to dr dt. Don't call it Dr. dt. I always want to do that. Now we can interpret our answer. The radius is growing at 3 over 10 pi centimeters per second. And if we want to change that to a decimal number, it might make more sense. So we see some patterns here. The key is to just follow this 9-step process. There it is. All right, so now we have the radius of the circle is decreasing at a rate of 3 centimeters per second. It's getting smaller. How fast is the circumference changing when the circumference is 18 centimeters? So the rate of change, dr dt of the radius, is negative 3 centimeters per. Oh, that should just be centimeters per second. My bad. Quick little save. Go back. Centimeters per second. How fast is the circumference changing when the circumference is 18 centimeters? So we know the rate of change of the radius, dr dt, is negative 3 because it's decreasing. And the circumference is 18 centimeters. All right. We're good this time, since we're talking about circumference, we're going to use this formula. Taking the derivative. Now, the derivative of pi is a constant, so we don't use the product rule. The derivative of 2 pi r, well, the derivative of 2r is 2 dr dt. So the derivative of 2 pi r is 2 pi dr dt. The derivative of circumference is dc dt. So dc dt equals 2 pi dr dt. Now we know dr dt is negative 3, and the circumference, it doesn't even matter because we know what it is, but it's not in the formula. So dc dt equals 2 pi times negative 3, or negative 6 pi dc dt. So it doesn't really matter what the circumference is. It's always shrinking at a rate of negative 6 pi centimeters per second. Now, circumference is the distance around. So it's a distance. It's one dimension. So the circumference is shrinking at negative 6 pi centimeters per second. Boom. Let's go on to another one. Okay, now we're dealing with a cube, 3 dimensions. The edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters long? There's our cube. All right, so it's got length, width, and height, and are the types of edges. So each edge is x. So it didn't come in one at a time. Just pretend that it did. So the rate of change of x with respect to t is 2 centimeters per second, and the length of each edge, which would be x, is 50 centimeters. Now we're going to use the volume formula. Volume equals x cubed. Length times width times height, x times x times x, x cubed. Taking the derivative of both sides. The derivative of v is dv dt. The derivative of x cubed is 3x squared dx dt. We're going to plug in for dx dt is 2, and x equals 50. What the heck? All right, 50 squared is 2,500. 2,500 times 2 is 5,000. Times 3 is 15,000. I apologize. So it should be 15,000. And this should be 15,000. Save that. I can't believe that. So once again, we have a cube. Edges are all x. X is growing at a rate of 2 centimeters per second. And so dx dt is 2 centimeters per second. and we're considering when x is equal to 50. So we see that our dv dt is equal to 3x squared times dx dt, and we know dx dt is 2, and x equals 50. So we're going to plug and chug. So we have 3 times 50 centimeters squared times 2 centimeters. Now, the reason why I want to spend some time here is for our units. Volume is in 3 dimensions. So here we have centimeters squared times centimeters would be centimeters cubed per second. So the volume's changing at a rate of 15,000 cubic centimeters per second. So the volume increases at a rate of 15,000 cubic centimeters per second. Of course, we circle it. All right, now we're going to have some problems with spheres that we're going to see later, but basically I wanted to show you the formulas for spheres. The volume of a sphere is 4/3 pi r cubed. If we had to take the rate of change of the volume, would be take this 3, throw it out in front, and the 3's cancel. So it's 4 pi r squared dr dt. Don't call it Dr. dt. And the surface area of a sphere is 4 pi r squared. I bet you didn't know that the derivative of volume is surface area. So since the surface area is 4 pi r squared, the rate of change of surface area would be dSA dt equals, take the derivative, 8 pi r dr dt. Oh, that's a shame. So we'll come back to spheres in a moment. A rectangle initially has dimensions of 20 by 90. Width is 20, length is 90. The width increases at 5 centimeters per minute. So dw dt is 5 centimeters per minute. The length shrinks at a rate of -3 centimeters per minute. So dl dt is -3. At what rate is the area changing after 15 seconds? So 15 seconds later, what is the rate of change of the area, or dA dt? All right, so area is length times width. Now, after 15 seconds, so if the width is growing at 5 centimeters per second, 5 times 15 is 75. Add that to the 20, and our width after 15 seconds is 95. Our length is shrinking at a rate of -3 centimeters per second. So after 15 seconds, it would have shrunk by -45. If it was initially 90, 90 minus 45 is 45. So after 15 seconds, the length is 45. That's all what that means. So the width is 20 plus 5 times 15, or 95. The length is 20 plus -3 times 15, or +45. dl dt is -3. We know that already from here. dw dt is 5. We know that from here. And we're going to start with this formula, take the derivative of both. Now we're going to have to use the product rule. 1d2 plus 2d1. So dA, oh gosh, that should say dA, oh marron. Okay, so dA dt, I do it here too. So dA dt equals 1d2 plus 2d1, L dw dt plus w dl dt. Now we have all these values. Look at this. L is 45. dw dt is 5. W is 95. dl dt is -3. So we have one unknown, dA dt, the rate of change of area, which is what we're trying to find. So perfect. So plugging and chugging. 45 times 5 plus 95 times -3 equals a total of -60. What does that mean? Now let's do it. After 15 seconds, the area is shrinking at a rate of -60 square centimeters per minute. Perfect. Hope that makes sense to you. One final problem. Back to spheres. Okay, you're going to see this one in the homework. A spherical snowball melts at a rate proportional to its surface area. What the hell does that mean? We're going to learn in a second. Show that the radius is growing at a constant. So melting means the volume is changing. Volume changing means dV dt. So since we're using this formula, we take the derivative of that formula and we get dV dt equals, take the 3 out in front, 4 pi r squared dr dt. We learned that from the other slide. Proportional to surface area means that, so it says the change in volume is proportional to surface area. Surface area is 4 pi r squared. Proportional means you throw a k out in front. So the change in volume dv dt is also equal to k times surface area. So up here we have dv dt equals 4 pi r squared dr dt. Over here we have dv dt equals k times the surface area. What's surface area? 4 pi r squared. So we have dv dt equals k times 4 pi r squared. And over here we have dv dt equals 4 pi r squared dr dt. Let's take these two dv dt equations and set them equal to each other. So set the two dv dt equations equal, and we get this expression right here is equal to this expression right here. So 4 pi r squared dr dt equals k times 4 pi r squared. All right, we are going to listen, and listen more. We're going to divide both sides by pi r squared. And what do we get? dr dt on the left side equals k on the right side. K is a constant. So the rate of change of radius is a constant. What do we want to show? Show that the radius is growing at a constant. That's what we just did. Ooh, there it goes again. So the radius is growing at a constant rate. All right, that ends the new material. So on Monday, we're having our test. You have all the review information. Today's problem set is due November 18th. And the November 18th problem set, since we have a test on the 21st, won't be due on the 21st. It'll be due on the 28th when we come back from Thanksgiving break. All right. And our resources, here's the key to today's problem set, and there's the pages to today's problem set. All right. Have a nice day, everybody.